So let's continue on the session 2. I may apologize first if you hear any noise from the lightning and rains. So right now it's rain a little bit in Rayong. So okay, so let's get to the next problem. So this problem, let's read through together. We have two boxes and we have this box B on the top, and then we have weight 30 pounds on the bottom. We call A, object A, and which is supported by horizontal surface here. And please also highlighted this, no frictions. Okay, and A, find the acceleration of the weight, and B, the acceleration of the block relative to the weight A. Okay, so let's move to a side. Let's start. Okay. No. So weird that okay, so anyway, let's start. So let's first again draw the free body diagram, FBD. First, let's start with weight on the bottom first. So this one we have object A. Okay. And then, okay, so first we drawing the force. We have wedge A and okay, then we drawing the coordinate, so we using coordinate y-x like this, and then we also starting to draw the force by the support N2, because we have also N1 here, right? And then there is no dimension related to this, and we don't know, we don't write any dimension, and then we draw kinetic diagrams, KD, then we have only this, MAAA. Okay, so right, then let's see the question. There are acceleration on the weight. So first we would like to find AA, and then next acceleration of the block relative into weight. So we have to find the acceleration of B respected to A. So is this the acceleration of B when you are standing on the A, right? And next, so okay, then first we have to solve the equation again. This one we draw fx equal to 0, no, sorry, equal to ma and acceleration A And then here in this case we have this as, okay, this is 30 degrees, right? Then this n is n1 sine 30 equal to MA AA, and then that means 0.5 N1 equal to WA over G, acceleration A. Okay, and later we will substitute later the WA, because we have the WA as 30 pounds. Let's do it. So we have 30 pounds over 32 point, I think 32.2, right? That's 32.2 feet per 6 square multiplied by acceleration A. Okay, so next we continue on. Let me again take a look. Oh. Okay, so alright, then next we object B. We're starting from B. We have the B object. Then we have weight of B. Then we say the plane is like this, y-x, because otherwise it depends on you whether you would like to do it on the normal plane or you do it like this. Then for the KD you have also the same like this, and we have what? This MA. Okay, and then we have also MBAA. So we have two acceleration here. Why? It's because your objects here, you have your own sliding acceleration. This one, this is your own sliding. And then you also have the sliding from the object below. So because the wedge A here is also moving. So that's why you have accelerations, two acceleration in here. But in the end, those two accelerations, you can also write like this, that you have only one, but you are not know the direction yet. You can write like this also, MAAB, because AB is equal to AA time AB respected to A. Okay, but anyway, we will focus on this pictures, right? So next, for this part, we have sigma fx equal to MBAB, but it actually MBAA cos 30 minus AB respective to A, and then in the end you will get the WB, and that is also minus because your force is in the negative sign here. but then you have to sign 30 to make it into the coordinates, and you have to build b over g again, and then a cos 30 minus ABA. Okay, then in the end, when you solve all of this, you will cutting this out, and then you will have ABA cos 30 plus G sine 30. Right? So here is your, this is equation 1, this is equation 2 that you will use in the future to solving this. And then here is your equation 3. You already used that. And alright. Then we have also to solve sigma Fy on this B object equal to MB and then AY. We have to solve this because we would like to know the normal force N1. Right? And then we will have here as N1 minus WB cos 30 equal to negative WB over G, and then everything multiplied by A sine 30. This will be equation 4. And then to solve this, you will plug the 1 into 4, and then you will get 2 you get 230 over 32.2 AA, and then minus WB, I will substitute this later, cos 30 equal to negative WB over G AA sine 30. Is it N? This is how long you can go for the node? Possible. I don't know why. But I hope it is not the end. Okay. Right, and then you have AA equal to 32.2 times 12 times cos 30, then everything 230 and then plus 12 sine 30, and then in the end you will get A equal to 5.07 feet per sec square. And then you know that ABA equal to A cos 30 plus G sine 30. Then this ABA is equal to 5.07 cos 30 plus 32.2 sine 30. And then in the end you will get AB. No. Sorry for this stumbling. ABA. Okay. This is equal to 20.5 feet per second square. So, no. So I will creating. Okay, so leave it like that. So we creating a new one, no problem. Lecture 9 part 2, enter. Okay, means we have acceleration A, as 5.07 feet per sec squared, and we have acceleration BA equal to 20.5 feet per sec squared. And then what does it mean here? Means you have your movement of AA here, and then here is the individual movement of acceleration BA. But acceleration B respective to A means you are standing on the wedge BA and then you see B moving. Okay? Then that's it for this problem. Next, let's get back to the presentations. Okay, previously we do the kinetics on the coordinates, for Cartesian coordinates. So we have two components, or if it's 3D then we have three components, x, y, z. But then here we will do it on normal tangential coordinates. Okay, then let's see the example. The tangential means you have this force inward here, we call it normal, and then we have tangential plane as t. Let's see in this equation of motions. So we have tangential components. This one you can remember. For the tangential side, we have F equal to ma, and then the tangential is like this, so it's just in this directions. And then for normal plane here, we have a direction as this in plane here. We have direction inward. Okay, and then acceleration is always an equal to v square over r. R is the arm length between the middles to the tangential coordinate there, tangential line there. Okay, so this is R, right? Then next, so let's get to the real problem here. I may do it. Let's see. No, sorry. Okay, so we have the bob of 2-meter pendulums. So have you saw this in the physics lab, maybe in the high schools, that we attach the ball here to the rope, and this is swing back and forth. And here again, sorry for the noise from the rain. Maybe I hope it will get less noise as the time pass by. And if the tension on the cord is okay, the tension is on the cord is 2.5 times weight, mean the tension here is T equal to 2.5 mg. Okay, and then the weight of the ball and the position shown, and find the velocity and acceleration of the ball in that positions. So let's see. Sample of length 12.5. Okay, so we have this pendulum. And then this is 2 meters. And then here we have 30. And then when we draw the body diagrams, you have ball, and this is the line, and then here is end plane, and here is T. We have weight here, W equal to mg, and here is 30 degree, and we have a tension as T equal to 2.5 mg. And then for KD kinetics diagrams, we have easy MAN, and we have MAT. Okay, so let's solve the equation one by one. Sigma F tangential equal to M acceleration of tangential, and then in the end is equal to mg sine 30. As you can see, we have to project this. This is 30. Then you have to project this to this, and then okay, this one is equal to m at, and then at will equal to g sine 30. And then at in the end will equal to 4.9 meter per second square. And next we do for the normal plane MAN, and then this is, we know that this is tangential T, but actually 2.5 mg here, and then we negative because it's in the negative sign for this weight, and this is mg cos 30. So mg cos 30 equal to MAN, and in the end AN is equal to G 2.5 minus cos 30, and AN is equal to 16.3 meter per second square. Okay, and to find, now we got already the acceleration in both sides, but they also ask for velocity. So the velocity, you can just find it from this formula. So velocity equal to ANR, and then square root means we have 16.3 times 2, and then we got plus minus 5.66 meter per second. What does it mean here? Means when our pendulum has tension equal to 2.5 mg, sorry, we will have the speed of 5.66 meter per second. Okay? Yeah. So next we will continue to the next topics. So for kinetics, we also have radial and transverse coordinates here. Okay, so previously it's about the pendulums, where you always have R as the same, but here we will talk about the radial and transverse. Let's see what this is about. First, for example, this is about the hydraulic actuators. Have you ever seen this kind of machine before? So we have an arm here. It can move like this, and also it can move also extended this one up and down also, for example. Okay, let's see what this is about. And also when you have some kind of this, you also have this hydraulic module which can also be tracking. For example, you can, or it's maybe longer, for example. Let's see. So in these things you will have the formula similar to what we learned before. We learned Cartesian coordinates, we learned about normal, tangential components, and then here we also have radial and transverse components. Okay, and here is the radial part, and here is transverse part, and here is the formula to solving the problem. Okay, so you can see that the difference from this one and the normal and tangential is that this one doesn't mean your R is fixed. You can see that if you are in this point, your R will become bigger than R1. Okay? But anyway, you have the movement in radial, you have a movement in angle, and you also have a movement in transverse. Means you're not only changing the angle, but you also changing the length. You can see if I draw it, the circle is like this. If it like this, then it's become, if it move along this, let's see what do I have. If it move along this red curve, which is R is constant, then we can use the normal and tangential coordinates. But if it's not constant here, we have also transverse directions. You can see the length here different. So you might also change that coordinate to the radial transverse components, right? So okay, so this is delta R, sorry, this means this is R. Let me make it more clear for you. This is R2, and then this R2 is equal to R1 plus delta R. Alright? So, okay, but in the end, in this one, if you are interested in, you can ask me directly. When you can also email me or call me if you have any question into this chapters. But anyway, in this radial and transverse component will not be also in the exam, but if you are interested in, you can also study and ask me. Okay, so I think, okay, the next one is angular momentums. For example, we also have the satellite orbits are analyzed using the conservation of angular momentums. So we will have also the, how to say, you remember the momentum that we learned before, mv? But here the momentum is in the angle. So here will not be V anymore. It will be in the term of this angular. Okay? And this is all the formula again for this one. So in the end, if you are interested in, you can also ask me more about this one, but please also prepare and also send me the assignment from the last chapters. I think only a few guys sending it to me. Okay, so that's it for today. Thank you very much for the attending, and also hope you stay safe for the situation right now for the COVID. Please stay safe and stay home and be healthy. Bye bye.